right, we'll go ahead and get started here, so we have plenty of time for questions at the end. So I'm thrilled to introduce Tovi Grossman, who is here from Autodesk Research, where he's a distinguished research scientist. He's also soon to be faculty at the University of Toronto. Tovi is certainly a staple in the CHI and WIST community. He has I learned this from your bio, more than 90 papers at CHI and WIST with 14 best papers and honorable mentions. We can all strive to get there at some point in our careers, hopefully. He's also been the technical program co-chair for both CHI and WIST in the past. So today Tovi's going to be talking about some of his new work on kind of thinking about interaction with new technologies and how emerging technologies can be used to enhance learning and knowledge sharing. So, perfect.
Thank you.
Well, yes. Oh, yes. That's right. Let's push that button afterwards. One job. All right.
Perfect. Thanks a lot for that introduction. I'm really excited to be here. This is my first time on campus, so it's really great to see the area and meet the people and see the lab space that you have here. So as Walter mentioned, I'm from Autodesk. This is a picture actually of our brand new building that we have. We've just moved into a central location of downtown Toronto at Autodesk, and as Walter also mentioned, in July next year I'll be moving to take on a position in the computer science department at the University of Toronto. And the nice thing about this is actually these two locations are approximately a 5-minute walk from one another, so I still hope to have a strong tie-in with industry and with Autodesk. And actually, just a short pitch for Toronto HCI Research is we have this newly formed Tux group, which we started about 2 years ago. And it's basically a place for all members of the HCI research community from the greater Toronto area to come together, and we meet every 2 weeks, and that also includes a monthly speaker series where we have distinguished speakers come in and give talks. So Toronto is a thriving area for doing HCI research. Before I jump into my talk, I'll just say, as a distinguished research scientist at Autodesk Research, my job isn't only to lead research projects, but also to define the main areas of research we want to do and form strong connections with the academic community. And so I'd like to acknowledge all the collaborators I've had over the years, including, of course, my colleagues at Autodesk, but also within the academic community. And that also includes a strong research internship program that we've had at Autodesk Research. So some of the projects you'll see today were actually conducted by research interns under my supervision at Autodesk Research. So the core area of my research has been looking at what we call technology-assisted learning. And my main mission here really is to help people learn to use tools in better ways and transition from novice to expertise. And later in the talk, I'll mention some of the other areas of research interests that I have. So just to give some motivation about this concept of technology-assisted learning, when I was putting this slide deck together, I had a separate Word document of some notes that I made that I wanted to use to edit the slide deck. So I went down to click on the Word icon in the taskbar, and unfortunately I got what I'd call this, icons of doom, right, in the taskbar. By the time I figured out which Word document was that had the notes, I'd lost the train of my thought. What I've since found out is that instead I can hold down the Control button, and this is a trick you can all thank me for later, and when you click, you actually get the last document you were working on. So it's a pretty cool trick. Since finding this out, I've actually used this all the time. Now, this type of thing doesn't just happen in software; it happens in the physical world too. So for tasks that we might think we're pretty good at doing, we actually find there's better ways of doing it, such as this 2-second shoelace tie. Or this pretty nifty way to separate eggs, which is a lot better than my technique, which has about 50% success rate. So this sort of just shows the concept of there's always opportunities for us to learn and improve our capabilities, both in software and in the real world. Now, be honest, when you see a dialog box like this, where's the first place you would click? Close, yeah. Or maybe uncheck the show tips at startup so to ensure you never see this again, right? We found lots of examples of this in the software industry, right? Clippy is a very famous example, and this also failed. So a lot of people are trying to develop technologies that can help us learn, and specifically in software, people aren't using them, they're closing them. And this is the problem that I really wanted to solve, and create a sort of system of just-in-time learning where we can provide not just intelligent ways, but friendlier ways than this that actually are distracting or disruptive to help people with their learning challenges. And I actually got interested in this just in the end of my Ph.D. research at University of Toronto, where I did this project helping people transition from using the novice method of using menus to activate tools to using hotkeys. So you can see here it's actually giving a hint of what hotkey to use execute a function. Or you can actually be a little bit cruel and add a delay to them if they select something from the menu. Or you could be really mean and disable items altogether. So in this case, the user tries to execute a command using the novice method, and they're actually being forced to use the hotkey to continue. So that's sort of going to the extreme. But the interesting thing is that what we found in this graph shows performance over the time, you can see in the control condition, they're actually faster at the start than using hotkeys because there's sort of this mental workload that was required. But in the long run, using these hotkeys was more efficient. And so it's an example of using technology-assisted learning to help people improve their performance over time. And this really sort of settled in with me that computers are not just tools that help us complete our tasks, but they can sort of augment our learning processes and our knowledge about tasks that we're trying to accomplish. And I, for one, know a lot about sort of world geography from my work. I don't know if anyone's old enough to recognize this, but it's Where in the World is Carmen Sandiego from my grade 3 computer lab classes, which is what all I did was play this game. It's sort of an early example of technology-assisted learning, but it actually goes back much further than this. So this is Edward Thorndike, who is sort of considered one of the founders of educational psychology. He has this really amazing quote. It says, "If by a miracle of mechanical ingenuity, a book could be so arranged that only to him who had done what was directed on page 1 would page 2 become visible, and so on. Much that now requires personal instruction could be managed by print." So this, to me, is a really seminal statement both in HCI and technology-assisted learning. And actually a lot of technologies that are still used today, such as interactive tutorials and instructional scaffolding, is really based on this core concept. And even before the development of computers, psychologists were developing what they called these teaching machines that were immersed in the classroom, helping people or children to learn. And so just like these mechanical tools, I'm really interested in computational tools that can help people learn. And sort of one of the main observation is that as the technologies improve and computer science findings improve, so too do the ways in which we can learn. So you can think about the sort of evolution of technology and how this impacts the opportunities for learning. And we're at a point today where we essentially hold limitless access to information in the palms of our hands. Now, the challenge is that access to information isn't sort of sufficient for learning or for good learning to occur. And Carol, who was at IBM Watson Research Center, wrote this really interesting paper about the paradox of the active user. And he said that focusing on task completion reduces their motivation to spend any time just learning about the system, so that when situations appear that can be more effectively handled by new procedures, they are likely to stick with the procedures they already know, regardless of their efficacy. And this really gets at the point of that, when we're immersed in the task, we don't really want to take the time to step back and think about, is there better ways of doing this? Can I take some time to learn about this? And this escalates to today's software, which can have hundreds or even thousands of commands. So this becomes a really challenging problem. And so being at Autodesk for me has been a great opportunity to explore this research agenda and not just look at some of today's most challenging and complex software tools, but also have real-world impact with the research that I've been able to do. And as a computer scientist, we have the opportunity to look at not just the evolution of technology, but the sort of newest areas of computer science that are coming up and apply those to the domain of software learning. And there's sort of two core principles that we've identified that are sort of most promising and have sort of driven us to really compelling learning environments. One is that technology today can be used to instrument the learning environment. So doing things like metadata capture, capturing video, and doing context recognition. And the other core principle we've looked at that technology can do today for us is provide a connected environment where you're not just an independent learner, but you can be connected with a community of learners or a community of experts potentially, and you can do different types of knowledge sharing. And the most compelling learning experiences we've found, and which I'll call next generation learning for this talk, are those that combine these two core properties of being instrumented and connected. So in the rest of the talk, I'll talk about how this applies to software learning, but then also talk about how we can break out of just not only applying this to software, but to learning for physical tasks as well. So for software learning, there's sort of three challenges that we looked at in sequence. And the first was, how do we get users to even become aware of the tools that they should be learning about? And we already talked about this dialog box. So let's talk a little bit more about why something like this fails. Well, most of these sort of tip of the day type prompts take nothing into account about who you are or the context you're in. They don't know what you're trying to do. They don't know what your expertise is. They don't know what you know, what you need to know, things like that. So what we did was we thought about, can we provide an instrumented system that would collect all the information about what you're doing with the software and connect you with the community of users to more intelligently provide recommendations to you. And we can use like recommender system technologies such as like Amazon and Netflix to do this. Now the challenge with doing this is we don't really know what the ratings are. So like in Netflix and Amazon, they have some sense of ratings or a heuristic that does that. But for software, it's not clear what that means. So what we did was we actually took the command data that's being streamed back to the company by the people who agree to, when you get that box sometimes of, do you want to help improve this product? The companies actually get that data and store it. So we've collected all this data, and we basically thought, can we use the frequency that people are using commands as sort of an implicit rating? Now there's a problem with doing that. Can anyone predict what the most common command in AutoCAD is? Undo, yeah, pretty close. It's actually erase. So this is a visualization that one of my colleagues at Autodesk Research, Justin Mythical, did, showing all the commands sort of sorted by their frequency of use. And you can see it's really, it's dominated by these commonly used commands. Actually, erase isn't just the most common command. It's the most common command after erase as well. These are then the next three common commands. So people are erasing a lot in AutoCAD. So if we use these commands to drive recommendations, people are going to get very generic recommendations. So instead we use something called, from the information retrieval literature, called term frequency inverse document frequency, where you weight the importance of a term based on how often it's used across an entire corpus of documents. So what we did was we applied that to software commands. So the first step is you calculate the command frequency that a command is being used at. And then you calculate what we call the inverse user frequency. So how often a command is being used across the entire user community. And then you can multiply those two terms to get the command frequency inverse user frequency. So you can see at the chart at the bottom, that 3D align command is basically being amplified for this user because across the whole community, which you see in the middle, it's not being used very much at all. So we take all those command frequencies and then we can do collaborative filtering on this. And so the general idea is if we have a user who has never used a specific command, we can compare that user to all other users to calculate a similarity, and then do a weighted average based on the similarity value of that user to the n most similar users, and calculate what do we expect, what is sort of the expected frequency of that command. So when we did this, we ran a study, and that's the algorithm I just showed you is a standard user-based collaborative filtering algorithm. There's also an algorithm called item-based, where you do the same, but you're comparing items as opposed to users. And we compared this to Linton's algorithm, who basically took an aggregate of all the commands and recommended the top command instead of doing a sort of a user-personalized command recommendation. Now, an interesting thing about doing HCI research is it's not just the algorithms that matter, but you have to think about the design as well, and Clippy is a great example of that. What we did, instead of having a dialog that would pop up and distract people, we just sort of placed these command recommendations ambiently in the bottom right corner of the display. So it doesn't take up very much screen real estate, and it's never going to distract a user. They can refer to it if they're interested, otherwise they can ignore it. This is just a quick video showing the interaction behavior. So as a user works with the software, they can see this list, and once in a while the list will update based on what commands they use. If they use a command in the list, it'll get removed. So by definition, it only shows commands that you haven't used. You can hover over them and get more information about them. And if you do find a command that is not useful when you hover over it or inspect it, or maybe it is something that you have used in the past, you can click that X button on the right and dismiss it. So we deployed this system in a 6-week field study. And what we did is, for the first 4 weeks, we just captured the usage information, and then for the last 2 weeks, we activated the plugin. And we found that it did significantly increase the number of new commands that we observed people adopting with the system. So it's a nice example of showing this sort of connected and instrumented environment to drive learning of the tool. Now, once you become aware that we still want to look at how do you become a master of the tool or an expert with that tool. Now, what we did observe is there's actually already a domain of software that does an extremely good job of helping people learn. And in its case, those people learning could be children or they could be 65 years old. Does anyone know what industry I'm talking about that does such a good job?
Video games?
Video games, yeah. So here's my favorite example. This is called Plants vs. Zombies. This is level 1 of Plants vs. Zombies. The idea is you don't want to let the zombie get to your house. They've designed this first level in a way that it's basically impossible to fail. Okay, you drag the plants onto the lawn and the zombie will get killed. So they've used this sort of principle of scaffolding to make sure you have success at the early stages and build up complexity as you go along. Another great thing about games is that they can be online. So this is League of Legends. Interesting thing about online games is you're now competing against other people. You have a chance to observe what it is that they're doing. It's to the extent that thousands of people are flocking to these arenas to watch people compete. Now, some of these people are there for entertainment, but other people are actually there learning about what these experts do. And we wanted to think about, are there ways to bring this into the sort of more generic software industry? So we actually did a study where we brought people into our lab and developed this multiplayer game for AutoCAD, where people would have to do individual tasks with tools, but it was sort of a friendly competitive environment, where you would do a task, but you would be paired up with an opponent, and you would see which of you could complete the task first. Now there's two keys to this. One, after each task, you had a chance to review what it was your opponent did. If they happened to do better than you, you could see what sort of tricks they used, or how they accomplished the task before you. The other trick is how we paired people. And you can kind of describe it with this bipartite graph here. So you can imagine if we ranked all 8 users from the best P1 to the worst P8, there's a number of different ways you can pair them up for this type of environment. So this is what I'd call the Final Four, or the basketball tournament format, where the one faces 8, etc., etc. In this case, you're going to have half the people playing down in expertise, so they're not going to have a chance to really learn from people who are slightly better than them. You can also have what I call the weekly chess club model, where everyone gets in a room and you find someone who's of a similar level to you, and you play against them. But again, you still have half the people who are maybe it's closer now, but still playing down in a level. You don't have that chance of everyone sort of upskilling. A nice thing about doing this virtually in an online environment is you can actually sort of cheat. So what we did was we paired everyone to someone else who was slightly better than them, except for the first place player who would play the second place. So we studied this in a controlled setting, where we brought in 8 people who had never used AutoCAD before, and we gave 4 of those people a short amount of training on how to use the trim command, which is what we wanted them to learn within the context of the study. And additionally, we sort of injected 2 sort of hidden hints that aren't immediately obvious about this tool. So those 2 people in red learned about one hint, and the 2 people in blue learned about the second hint. So we ran the study, and everything sort of happened organically. The matching happened automatically. People were free to observe what their opponents were doing or not. And a really interesting thing happened is by the end of the study, all eight of the users not only knew how to use the trim tool at this point, but they all knew about both of the hidden hints that would not be immediately obvious. And what's actually even more interesting is that the users who were initially untrained were actually outperforming the experts by the end of that study. It really shows this potential of sort of knowledge diffusion in these sort of collaborative settings, which was not the case in the baseline setting, where there was no there wasn't these sort of gamified mechanics where you're being matched up with other people. So that talks about sort of mastery of tools. So this was a game to learn individual tools. But I also want to talk about sort of mastering higher level workflows, which is very important for software. So for example, imagine I had this type of drawing that was done in an image editor, and we used paint.net, which is an open source application for this. And I had no idea where to even begin to create something like this, but I was very interested. So there's some solutions to do this. One is software vendors create tutorials, but there's no way you can create tutorials for every type of workflow that somebody might want to do. And there's also community-generated tutorials that can be hard to find, access, and they're difficult for people to to create. Now, what if instead, every time anyone in the user community created a document, they were also at the same time creating a tutorial for other people? So that's what we wanted to explore with what we call the Chronicle System. So with this system, what we did was we captured everything that a user was doing. We did a video capture, but we also captured all the metadata, the command, settings, dialog boxes that people were using. And at the bottom, we displayed an interactive timeline, so you can scrub the video, but you can also see the relevant commands or layer settings that people were using when they created each part of the document. And to go further, we allowed users to sort of interactively explore all the different areas of the document. So if there's one specific area they didn't know how to do, you can probe that area, and it would show you the relevant workflows associated with that one subset of the document and allow you to get immediate access to that one area. I won't go into the engineering details of this, but it's actually not a huge challenge, and this can be applied to most software applications without much instrumentation. The instrumentation in this example is you identify the history stack, which almost all software applications have. So this is the actual code from paint.net, and this is the type of code we injected into this system. So basically, anytime a new command gets pushed onto the history stack, we timestamp it and send it into our own API. In addition to instrumenting the commands, we instrumented the individual pixels, so the actual data of the document as well. So we divided the image into pixels, and for each pixel, we kept track of all the different times that it changed over time. And that allowed us to do the probing that I just showed. So if you go and click a specific area, it generates all the times that that specific area was changed. We can then do a simple clustering of those changes and display revisions for each area of that document. So here's a quick video showing that interaction. So if I'm interested in how this emblem got its glossy effect, I can click it. And this clustering is actually hierarchical, so I can click the plus sign and drill down even further until I get to the specific revision that I'm interested in, and then click on it, and it'll take me immediately to a video of that interaction happening. And I could also refer to the command line down below and see what commands were used to execute that. So as I mentioned, a nice thing about doing this work in the context of industry research lab is we can push some of our research into products. So this example is a research project that was published in the academic community, but was also transferred into an Autodesk product. It's now known as Autodesk Screencast. And it's been extremely popular since we released it. It's had over 5 million page views now, and 100,000 videos have been added by the community. So it really shows the power of instrumenting the software, but also connecting it with the user community. Because for a software company and for their community, this is extremely valuable to have all these resources that can be used. So I think hopefully this gives you a sense of how you can provide an instrumented and connected environment to provide compelling learning environments for the users. Just before moving on, I'll just say all this research has been published in the academic literature, and if you're interested in more details, feel free to contact me and I can give you pointers to specific papers. Now, after doing this sort of line of research, I was thinking, how can we break out of the mold of just applying this type of research into the software industry and apply it to the real world, to physical tasks? And so I'm going to talk now about how we can apply this to physical learning, adapt it to physical tasks, and also apply it to group coordination tasks. So the idea is this, we have tasks like this in the physical world that require learning, training, and education. And we wanted to know is, not just can we improve learning, but can we do it in a similar way as how we apply to software? That is, can we instrument environments like this? And can we provide connected environments when people are learning to do this? And the concept is kind of like how someone in the trades would learn through an apprenticeship mentorship model, where you're learning in real time as you're doing the task and getting sort of real-time advice and guidance from an expert. Now I see two technologies that will allow us to do this. And the first is wearables. So you can say that we ourselves are becoming instrumented by the use and deployment of wearable technologies, and they hold this immense potential to instrument not only our environments, but our bodies themselves. Now the other technology that I see as up and coming, and obviously huge in the industry right now, is the Internet of Things. And what this is essentially doing is connecting us with our environments, and also having the potential to connect us with our peers and with our community. So just like we did in the software industry, we can apply this concept of next generation learning to physical tasks. So let me give you an example of this. So I actually used to play baseball when I was younger. I played for the University of Toronto baseball team. So I know a little bit about baseball. I was a pitcher, so I can't be too harsh on this guy because I'm not as good at hitting. But I can tell you from watching this video, this individual is making some mistakes with how they're hitting while they're using this, this hitting apparatus here, which is meant as a training device. Now the issue is this training device is completely passive, right? It's not capturing what the user is doing. It's giving them no feedback. It's just letting this person repeat the same mistakes over and over again. Instead, it would be nice if we can apply some of the concepts I've just shown you to this physical scenario to provide instrumentation and connection to experts to improve the performance. And I'd say there's one sort of best-in-class scenario for doing this, and I refer to prior literature of Mr. Miyagi. So in the Karate Kid, there's this scene where Mr. Miyagi is teaching Daniel all these different physical movements that will eventually be used for martial arts. If you actually go back and watch this, it's actually really insightful about the richness of the interaction that these two have as Daniel is learning. So not only is Mr. Miyagi sort of demonstrating, he's also giving sort of real-time guidance or even feedback on what Daniel is doing to perfect the movements that he's accomplishing. So I'd really like to find ways that we can sort of replicate this experience without having to have a Mr. Miyagi behind us or beside us all the time. So a couple examples that we've looked at, and I'm not going to go into too many details, but one was the system which we called UMove, where we looked at the sort of training methods of dancers who use mirrors to see their own reflection. And in this case, they are getting some sense of feedback because they can see their own movements. But we went even further by instrumenting the system by having a depth camera capture what it is you're doing. And then we provided an augmented reality mirror, so we can actually project the skeleton of not only yourself, but of an expert user who has done similar movements. So you have an opportunity to review what it is you're doing and see the actual errors and correct them in real time as you're learning these different physical movements. We've also applied this to physical tasks such as makerspaces. So what we did was we took traditional makerspace and we instrumented all the tools, the display surface, the toolbox. There's even a 3D printer, and we knew what stage the 3D printer was at all time. And we could guide people through the task using a digital display that replaced the traditional workbench. And again, it was this example of showing sort of video clips from what experts have done with the tool that you're currently using to provide this sort of guided experience. So that just gives you a flavor of how you can adapt some of the concepts I've showed you for software into the physical realm. But I want to talk a bit more about this concept of group coordination. Because a lot of physical tasks, as you start to scale them up, become not just tasks of individual users, but tasks of many people working together. And so one example is the construction industry. Can we provide instrumented and connected learning experiences for construction? So one response is sometimes, well, these people are already experts, why do you need that type of technology? There's actually scenarios where you have novices coming together and doing this type of construction. And there's programs like Habitat for Humanity, for example. So I actually took my team and went to a build site to learn more about this. And we actually spent the day helping to build this house. And these are like volunteer-based programs. So you can imagine yourself like arriving to one of these construction sites and not having any expertise or background in the types of tasks you're going to be given. And so not only is it a challenge for you, but there's also a site manager that has to assess everyone that's come for the day and figure out what skills and expertise they have, and they kind of have to size you up and decide, can I give this person a power drill, or should they be like painting, things like that. So there's this real opportunity to affect this sort of real world practice that's happening today, and you need to provide that learning in real time. And so one idea we had is, well, what if when you arrive, you get some sort of intelligent system, whether it's a wearable or something else, that's guiding you along the way, and that's coordinating everything that's happening to make sure the process of the construction is happening in an efficient way, and leveraging everyone's unique skills. So it sounds kind of like science fiction. And in fact, there is a piece of science fiction called Distraction by this author named Bruce Sterling, who does a lot of science fiction writing. And in this book, he talked about a hotel. I'm not going to read this whole quote, but basically the idea was it was this concept of a virtual assembly of a hotel, where you dump all the raw materials on site, and each individual brick had an awareness of its surrounding and could talk to people. So if you were walking by and say, hey, can you pick me up and move me to the left, or put me on top of this? And over time, this sort of hotel just organically assembles itself. It's kind of an interesting concept. So we wanted to explore this further and determine can something like this actually work, and what are the associated challenges and opportunities. So we actually designed this 12-foot tall pavilion. We actually worked with a computational architecture team to design this. Is a pavilion structure. It's made out of bamboo, and it would be very difficult to assemble for novice workers. And we actually ran this at a design and architecture conference. So the participants of the build were actually going to be just people with no knowledge of the project that just had to come in, and we had to figure out a way to guide them through the process. And we did this through two ways. And again, we instrumented the system and provided a connected environment. So the instrumentation was through wearables, and the smartwatches gave people the instructions. And we also provided IoT sensors that was connecting the entire environment, and it was also connecting everything to a central, what we call the Forman Engine. Another interesting aspect of the process is that people had to work with these robotic devices to build these are essentially the individual bricks of the pavilion. And these structures were something that would be very difficult to create by humans, and they had to work with these complex machinery, in this case robots, to create them. So it just added another extra challenge with the project of having total volunteers work with these complex machinery to complete the task. So just to give you a sense of it, I'll show this quick video now. So this is the final structure after the 3 days of the conference. So the structure is sort of continuously built over time. And I'll just say this is a massive collaborative effort to conduct this project. And our group, the User Interface Research Group, was really interested in the overall interface of this guidance and coordination effort that was required. Just to go over a bit of the specifics of the project, like I said, the individual building blocks were these what are called tensegrity units made out of 3 sticks of bamboo that are held together with the tension of thread that's wound around them. And for a person to do that, it's very tricky, and we developed these robotic stations. But the volunteer worker would have to understand how to load the part onto the robot to have this winding occur. And the actual architecture of the pavilion itself was designed with this computational method. And the important thing to note is that each part that was being created was unique and had to go in the correct position to create the overall structure, which again creates a bit of a challenge for these novice workers who, for them, every part will sort of look the same. So I'll talk about how we accomplish this. So again, we use the smartwatches to provide guidance and instructions in real time. And there's actually location tracking within the system, so it would know where people were and know what instructions to deliver at the right time. And the way we provided like the location guidance of like, if I have a part, where does it go, is we actually embedded the IoT devices in the building itself. So these were small wireless LED devices. And we can illuminate them. Each one was individually addressable. So as a person needed to put a part on the structure, we'd illuminate the existing parts on the structure so they'd know exactly where to put it and what orientation to put it in. So this is the overall architecture. So we had this central, what we called a Forman Engine. So you think of it as a digital foreman that's doing all the heavy lifting of understanding what people are in the system, what stage of the task they're on, and what they should be directed to do next. And this is sort of a back-end simulation of what the Forman Engine was doing. So you can see it's keeping track of all the robots, what stage the robots are on. On the left there you see the LEDs. It knows what LEDs to illuminate at each time, and then it's distributing the instructions to the smartwatches And at the bottom there, it's also keeping track of the build and intelligently assigning new parts to people as they enter the system. And this is sort of an on-site dashboard that we developed for the exhibit and for the building of the structure. So people who were involved in it, but also just walking by, could see the progress of everything. So this is sort of more of a front-end visualization of everything that was going on with this digital Forman. And the nice thing about providing this sort of connected environment to do all this stuff is you have all this data available, so you can upload it to the cloud. So we actually developed a mobile app. People could check in and see the sort of the progress of the structure over time. And if it was someone who participated, they can actually see the individual part that they added to the structure, which you see in red there. And you can also, by providing this connected environment, this starts to point at the implications to the construction industry, is you can do all sorts of analytics in real time about the development of the project over time. You can sort of identify areas of challenges. You can identify areas of where people were actually learning or getting better. So there's some really interesting opportunities by providing a connected environment and having sensors track everything that's going on in a system like this. So here's the team that conducted this project. So there's about 30 people in total. And then on the right was my user interface research group that worked on the interface challenges that I just talked about. Now going further, this project, what was interesting about it was every person who entered the system basically did the same task. They got the raw materials, they built one of these modules, and they added it to the structure. So it was very sort of mechanical and almost predictable process. And what we wanted to think about was a more, not necessarily open-ended task, but collaborative task where everyone is going to be doing something slightly different, and how to efficiently coordinate people in those types of tasks. So we can hope to refer to instructions in cases like this, but unfortunately we know that instructions are not always the best. Now I'm not going to talk about the usability of these types of instructions, because that's a whole nother presentation. But the point I want to make is that instructions like this rarely tell you how to collaborate with your peers. Okay, so often, like if I'm building an IKEA kitchen, for example, I might get the instructions for all the different cabinets, but it's up to me to figure out that if I have a couple of friends over that are going to help me, to figure out how to sort of efficiently use everyone and leverage everyone's unique skills. Now, this is extremely important, and I'll give you a sort of an abstraction of why this is so important. So you can imagine if some task I have, we can sort of take all the subset tasks or subtasks that have to be done to complete it. And you add up all those times and you get a certain time to complete that task. Now, if we develop some new system to help someone transition from novice to expert, maybe we get some percentage savings of how long each subtask takes, and in turn the final task gets completed faster. But if we can instead find a way to have people coordinate efficiently and do the task together, you can have incredible impact on the overall efficiency of the system. And I have some really great videos to really highlight this. So this first video is one of my favorites. So this is a pit stop at a F1 series race. And it's probably one of the best depictions of coordination, group coordination that I've ever seen. And they're done. They're done for the day. That's it. So pretty amazing, right? 3 seconds. There was 22 people there. All of them were doing something different. They had to be perfectly coordinated. Now, obviously, these people have tons of training, right, and professional expertise to do this. But what they're able to accomplish when you have that level of coordination is pretty amazing. Here's another example that's sort of more applicable to the construction industry. This is called a barn raising or a raising bee. It's still actually used today, but historically it was used by communities where people had a barn, they wanted to put it up. They don't have all the heavy tractors that we do today. So you invite members of the community, everyone comes together. It's almost a social event, but it's it has a practical purpose as well, and it's incredible. This is a time lapse over one day, and there's a lot of Mennonite communities that are still using these processes. And again, the level of coordination that's required to do something like this is pretty amazing. And again, the people that are involved in this obviously have a lot of experience doing these types of things. And there is this sort of mentorship approach where people start off by the people down below just handing the materials, but then eventually you work your way up and you can take part in the more the processes that require more expertise. Now, I don't know if there's any software engineers in the audience here, but you're probably thinking about this sort of scenario. I'm saying, well, you just add more people and things become more efficient. And obviously that's not actually the case. And there's actually this seminal text by Brooks called the Mythical Man Hour, where he says adding manpower to a late software project makes it later, right? So that's sort of the core challenge that I want to look at, and I think is an opportunity that instrumented and connected environments can provide, is that by adding additional people to a project, if you have the proper technology and proper interface to do so, you can potentially reduce the overall time it takes to complete that project. So here's one way that we looked at this problem. So this is a system we published at CHI just recently, a system called WeBuild. And we looked at it was a smaller use case of you had to assemble this table, you had to build all these Lego structures and build these custom platforms out of pieces of wood and nails to rest the Lego on. And what we did was we took that entire task and we did a decomposition of every single individual subtask that was required to complete that task. And we modeled not only what was required for each task, but what tasks it depended on. So it creates this sort of task dependency tree. And actually, this is something very well known. It's called the resource constrained project scheduling problem, where you have, you want to find a schedule of minimal duration by you assign a start time and a duration for all the subtasks, and you need to honor the precedence relationships, and also honor the resource availabilities that you have for completing the task. So in this case, the resources available are the people, but also the tools that are required for each task. This is actually known to be an NP-hard problem, so it's a very complex optimization problem. So what we did was we used a heuristic approach using a greedy algorithm to try to solve this in a somewhat efficient way. So like I said, we sort of decomposed each task into the tools and the skills that were required. And for each subsection of the task, we knew what tools were required, the skills, but also the minimum and maximum number of people that could help with the task, and also the dependencies on other tasks that were required. And then we also looked at the similarity between two different steps in the overall build. And that way we could track people's expertise over time and assign them to tasks that they already showed that they were pretty efficient at doing. So just very briefly, the heuristics we had for this algorithm, we looked at basically when we kind of did it like a step-by-step approach. Every time you completed a subtask, you'd be assigned to a new task. And these heuristics sort of helped us point to which task they should be assigned to. So the depth of the tree is like, how far down the tree is this subtask? It should probably be done sooner if it's further down. We also looked at the individual expertise people had. Continuity, meaning if I just assembled a piece of Lego and there's another piece to go on it, I should probably do that task because it's sort of a continuous nature instead of jumping to something else. We also looked at sort of tunable parameters. So when you're doing a build like this, you might want to bias towards group work. So if, for example, when you assemble the table, it could probably be done individually, but maybe it's better if a group works on it. And you can sort of tune that and decide you want this to be a collaborative effort or you want people to be working individually. And the other tunable parameter we had was looking at repetition versus diversity. So if you go back to the Habitat for Humanity example I showed you, you could arrive on site and be told to sweep the road for the entire day, right? And no one would probably be very satisfied with that type of experience, but it'd still be extremely useful to the overall build. So this is just sort of a parameter that might not impact overall efficiency, but just change the sort of qualitative properties of the experience for the people. Now, similar with the project I showed previously, we were using mobile devices, in this case, smartphones, to deliver the instructions. So everyone in the system would have their own phone. It would deliver them what instructions and what step they should do next. And they would click a button when they confirmed that they had completed that step. And this way, we were able to sort of monitor over time how efficient people were with each task. And then the overall architecture was, again, very same. We had this central server that was recording everything that was happening, keeping track of the overall process of the task, and distributing those tasks to the phones. And here's a quick video showing the study we did. And what's really interesting, the most sort of dramatic data we got from the study was the overall start time. So people with our system, basically as soon as they sat down, they were ready to go because they were getting the tasks that they should do and they started working. Whereas in the control condition, there's that sort of startup time where you really have to figure out what everyone's going to do, what the overall strategy should be, etc. And this sort of, you could observe it throughout the entire 20-minute build, but it was most dramatic right at the start of the task. So again, these examples show how providing an instrumented environment and connecting you to other experts or other people in the environment can provide next generation learning for physical tasks. And just like the work in the software, this has all been published in the academic literature. And again, please feel free to come up and talk to me if you want any more details or pointers to specific papers. So before I wrap, I just want to talk about some areas of future work and some of the other areas of interest that I'm working on. So in the future, I'm really interested in, again, like scaling this work up to real-world construction environments where having wearable devices, IoT devices distributed to people could have massive savings on efficiency, but also safety as well. The digitization of construction has already sort of started to occur. There's systems that sort of monitor sites through vision, but they're not really feeding that information back into the individual workers to help with overall efficiency or learning guidance, things like that. I'm probably most excited about this concept of volunteer construction, where you have systems like Habitat for Humanity. I think there's a real opportunity to understand the challenges at a deeper level and find technologies that can be used. And another really interesting one, and one that's very relevant today, is things like disaster relief. Going to places abroad where the workers might not have the skills, but they definitely have the people there that are willing to do this. And again, it's a matter of providing the right level of learning and guidance. One group I've started to collaborate with is called Better Shelter, and what they're doing is they've designed a shelter system for refugees, so that can be deployed to refugee camps. But they're much more robust than the typical tents that you have in refugee camps. And they've partnered with IKEA, so they fabricate these offsite, they flat pack them, and then they ship them off to the shelters. Now they have, when I was having my initial meetings with them, they expressed that their main bottleneck is the assembly process, because it's basically like, they sent me the instructions, and it's basically IKEA instructions, but for building a house. So you can imagine that, it's a total disaster. And there's this huge potential to use some of the technologies I talked about and apply them in this situation. Of course, situations like this, the solutions need to be low cost. So there's a lot of research in HCI looking at how you can deploy sensor networks, things like that, in low-cost ways. So that's something I'm really interested in. Just more broadly at a higher level, it's been amazing to see all the work, and including some of the work being done here on online crowdsourcing. And I think there's a real opportunity to apply some of the similar principles to what I call physical crowdsourcing for physical tasks. So I think this is an entire area of research that is rich for future work. One of the interesting aspects of physical crowdsourcing is that it's no longer augmenting computation skills, but you're augmenting physical skills. So instead of augmenting sort of our computation and thinking, we're moving from like physical skills to physical automation or robotics. And one of the students that I've worked with, Madeline Gannon, is looking at ways that humans and robots can work together sort of in an environment that's more interactive. So, industrial robots, this is an exhibit she did at the London Design Museum, taking an industrial robot and instrumenting the entire environment with sensors. And so just like the work I showed you where people were working directly with robots, I think there's a lot of interesting work where humans and robots can work together. This is just a video clip of what happens if you approach the robot. It actually starts to have a bit of a personality and approaches and interacts with you. So this is another area that I'm really, really interested and excited about. The other sort of high-level area that I think is exciting is just this idea of how education is evolving over time. We, think about like the initial type of education done in a classroom, how this has evolved to like online MOOCs, things like that. And what I see as sort of the next potential area is what I talked about is just-in-time learning, where you're learning on the job site as things are happening while you're working on a specific task. I think this is super relevant today just because of the sort of general trend towards the gig economy, where people are going literally from one job to the next in these sort of micro tasks that they get recruited for. And these are very specialized type tasks, but there's also sort of this like sort of larger gig economy out there and apps that aren't just for driving or for houses, but for all sorts of different types of tasks now. And again, this is going to be a challenge of how do we get people, as you know, in this sort of current market of job disruption through automation, where people's jobs are being replaced, they need to find something else to do the next day. How do you get them to learn in sort of real time on the fly? So I think this is super exciting. And finally, I'd say, like, what is the sort of holy grail, and something that we probably will never achieve, but something like this, right, where the matrix, where you're actually uploading information directly to our brain. So let's say, this is a great scene, right? He all of a sudden becomes an expert at Kung Fu. So I don't think we'll ever get there, but it's really interesting to think how close can we get using the technology that we have available. Just want to mention some of the other areas of research that I've been working on, and then I'll take some questions. So I'll talk a bit about the work I've done in dynamic illustrations. So we've been looking at ways of using sketch-based interfaces to provide animations or interactive illustrations. And you can see here there's different areas of work to not just add animations, but make sort of richer, fluid motions using sketch-based interface and actually interact with them, which you see in the top right there, where you just with a sketching interface you can interact with the elements. And this is another example of a technology that we actually deployed into actual products. So it's called Sketchbook Motion. So if you have an iPad, it's available on the App Store, and pretty fun to play with. It actually won the iPad App of the Year for 2016, which was kind of fun. My son complained he thought Super Mario Run should have won. Just other work I've been doing is on interactive fabrication, so looking at this idea of digital fabrication, how we can fabricate not just passive objects, but how we can fabricate objects that have behaviors or sort of digital components, things like that. And then finally, I've done a lot of work on body and wearable interaction, and I'm pretty excited now that I'm able to sort of merge the work I've been doing on learning with the work that I've done in the past on wearables, because I think there's sort of a nice complement and opportunity of combining the two. So with that, I will wrap up. Thank you for your attention, and take any questions you have. Yeah.
So I have a question about the tasks that you're helping people to learn. So one thing that makes the Chronicle so great is that, like, in the past, people have done studies learning like fixed tasks. So you have like now you like how to paint a fence or like how to build a very set house. But you're saying that this gamification is like on-demand work, where the work doesn't necessarily have a very set of instructions every single time. So I guess my question is like, what are your ideas for how to like create these instructions? Because even in the conference building the structure, you said you had to all this work to create the instructions to build this thing, but are you going to have someone do that for every single type of task, or how do you build in that kind of complexity?
Yeah, it's a really good question. So in the first example I showed with the 12-foot tall pavilion, like I said, all those instructions were pre-written. And in the second example, where it was like assembly of Lego or a table, things like that, we transcribed existing instructions for those two objects. So in some cases, instructions will be available, and you can do that sort of transcription process, potentially even automatically. There's actually a lot of interesting research now on taking a 3D structure and automatically generating instructions. So even if instructions never existed for that object before, they can, using machine learning and other algorithms, figure out what are the steps that someone might take to assemble this, and would provide the instructions. And then I think the other opportunity is what I showed earlier with the Chronicle Research, which sort of gets at that same problem, is that when you have a ton of commands in software, there's infinite ways you can combine them and do workflows. So the adequate instructional material for every workflow is just never going to be available. And what you can do is, if you start cataloging everything that everyone has done, you're probably going to find something maybe not exactly the same, but at least similar. So applying that to the physical realm, I think, is if you start instrumenting, for example, if we instrumented every construction environment in North America over the next year and catalog all the different skills people have and tasks and challenges that arise, then I think you will be in a better place to provide that real-time instruction when, like, oh crap, I was supposed to put this pipe here, but there's a duct. You'll probably find someone else that had that type of problem. So it's just like scaling up the pool of resources that you have. But yeah, it's definitely an interesting problem to look at.
I think this is a related question, but often what happens when you present to an audience with a lot of mixed background, you get disconnects in terminology. So you use several times the term next generation learning, but are you aware that there's a huge next generation learning project that's been funded by Gates, Hewlett, supported by EDUCAUSE, and so on and so forth, that really aims to use technology to innovate how teaching and learning happens, and in particular, to innovate learning models. So when you use the term, you're using it in a very, very different way than that community does, and it relates back to the conception of learning, I think. You very much have a transfer of information model of learning, right? And even your last example, the matrix kung fu thing, you said, I don't think we'll ever get there. That's a recognition by people like myself who know that learning isn't just about transmission of information. For tasks that are decomposable, where there are right and wrong answers and right and wrong steps, it works very well. But I'm not sure that it's broad enough to encompass a larger view of learning and other conceptions about how learning happens.
Yeah, okay, so a couple things there. So first, I was not aware of this, the next generation
Google
learning
it.
consortium, so I'll definitely take a pointer to that. But I also, like I said, for the purpose of this presentation, so it was just sort of a way to tie in all the different projects I've done that are using these components. But
Which is not to take away from your work,
Yep.
because you've done some amazing things.
100% agree that, especially a department like this that is so diverse. It's one of the nice things about coming to a place like this is you can connect with those different communities that you don't always see
And when we talk about connected learning in that community, we don't mean connected by technology. We mean connected learning as in connecting up the kinds of learning that happen in all different parts of our life, right? So informal learning activities with formal activities. So I'm just giving you a heads up that you've got some really key words there that another community sees very differently.
Yeah, and I mean, there's like obviously research on like organizational memory and like transactive memory, right? That are very similar again, and those aren't the terms that I use. So some of those theories and like you say, the models, like I am aware of those for sure, and yeah, absolutely. The other thing I'll say is this sort of concept of like learning versus like sort of knowledge transfer is very interesting, and I'd say there's definitely a discrepancy between some of the projects I've shown and what sort of deeper learning actually is and means. And a lot of the tasks I was showing are more procedural tasks that people need to do. So so that richer level of learning aren't necessarily a requirement, right? So example, the habitat building example. If we can find a system that provides that sort of knowledge transfer where they don't have that deeper sense of learning, but they've got enough to accomplish it in an efficient way, then that's probably sufficient. But you're probably right, I should be careful with how I define the terms around those environments. Yeah.
Okay, that's probably the last question.
Great.
Yeah. Going back to the Hive project that you had there, is that the name of it?
Yep.
Your infrastructure. Two questions on that. One, was there any differentiation in the skill that was required of the participants?
No, it was freely open to people that came in. The second project I showed with the Lego on the table, the smaller scale project, we did a very quick survey before people came in about what prior skills they had with different tools and things like that, and our system took that into account when distributing tasks. But for the Hive task, there was no prior knowledge or requirements for that. It was done at a conference, and anyone could sort of badge in, and they would just be part of the system at that point.
And then the second question is, did you observe anyone going, I don't know what this means, can you help me? How was that facilitated?
Yeah, for sure. Yeah, so I mean, the initial vision and hope was like, we would step aside and just let everything run itself. It's actually because of the robots that Autodesk Safety said, no, you have to be shadowing people just the whole time. So there were researchers within the system. So I would say there was very few cases, if any, where people said like, I'm stuck, I don't know what to do. Because we did extensive user testing ahead of time where we basically tested all the individual steps and made sure the instructions were sufficient. So there was a lot of like upfront work to make that happen, which you wouldn't necessarily have if you just run a system like this sort of in the open real world environment. But that's, yeah, it's definitely an important aspect of this type of work is the skills people have are so different from one to the other, and where people get stuck is hard to predict sometimes. Thanks.
All right, let's thank Tovi again. Okay.